before I get started, I would kind of like to know how many of you are using Postgres already. Okay, how many of you are using MySQL? Oracle? And MongoDB? Oh, quite a few. Okay, there's going to be a little bit of MongoDB stuff in there. So first of all, my name is Armin, and I work for a London-based computer game company, and we're mostly doing online services for games, which means that when you play a computer game, we make sure that you find other people. And we used to do a lot of MongoDB there, and we're now moving to Postgres for a variety of different reasons. But aside from that, I do a lot of Python. So on some of the slides, you might have a little bit of Python things on there. So I really like Postgres, mostly because from open source databases, the only alternative is running MySQL, and MySQL traditionally has some problems with some of the things that I use a lot, which is German language, and there are Unity code handling in MySQL has always been a little bit of an interesting experience. So Postgres is quite nice because it doesn't really do much with it, it just stores your data and that's it. And it also is very strict in regards to how it accepts data. So it's very hard to make terrible data in Postgres. It will warn or give you strong errors if you try to put anything that's not correct. On the other hand, we have MongoDB, which I had to use for the company I'm working. And MongoDB is just a thing where you store stuff in. And the reason, yes, if I'm too fast, just shout at me. So we used a lot of MongoDB at Splash Damage, and the main reason for that was that the team I work in is online services, and it's very far away from the game team. So a lot of the data that goes into our storage system comes from developers that don't really have any database experience. They're game developers, they just want to store something and they want to store it into MongoDB. And so they wrote something with MongoDB before we started working on it. So we already had some MongoDB stuff there, and it kind of works. So if you throw small amounts of data into MongoDB, you can almost ignore that there's a database behind it, and it will look like it works. But at one point, you have too much data in there, and you need to actually put database design behind it, like you set proper indexes, you need to make sure that the data is consistent, and it becomes a mess quite quickly. So we made a transition from MongoDB to Postgres over the last year, and it has been quite an interesting experience, especially coming. So I used Postgres before, but then I used MongoDB, and now we have a lot of MongoDB patterns on our Postgres database, which is interesting. So one thing that I find quite interesting is that a lot of the problems we thought we will have with MongoDB, we actually never had. Because our data set generally didn't become large enough that we ever had to use MongoDB. So the main reason we used MongoDB was because someone put it there, and we thought it's going to be, we needed to have big enough data, but we never actually grow our data set past 30 gigabytes. So our data set was too small to make sense for MongoDB. And even if it would have grown tenfold that size, we still would be able to fit into Postgres. So for us, it was actually quite easy to go to Postgres, not having to worry too much about having too much data. Postgres is really old. I think it's 30 years old now, but it's really good and well maintained. From Postgres 9.0 to 9.3, which is the current version, they got streaming replication, they got H-store support, I believe, that, which is a key value-based storage in it. It has incredible improvements on how it builds indexes now. So it got a lot better in just 6 years, so it's very actively maintained. And after MySQL got acquired by Oracle, a lot of people came from MySQL to Postgres because they were a little bit worried about the future of the project. So it got a lot of traction recently by new developers. And it's actually surprisingly modern. Even though it's that old, it has a lot of things in it which are very, very useful for what people do now, especially if you have applications or clouds and things. Alright, so just briefly, the reason why we use MongoDB for the most part is document storage format of it actually fits up quite well. And and we have largely non-relational data. So we have players, we have game sessions. They kind of belong together, but only for short periods of times. We have player statistics, which is just key value data, like number of kills per player. And we're quite write-heavy. So when the game session ends, we just blast a whole bunch of writes at it. So it really looked like MongoDB is quite good for that. And MongoDB also has this Mongos thing, or Mongo router, where you write to a local proxy, and that proxy then finds the appropriate database server and writes to that. And that really looked interesting until we had a whole bunch of problems with that. Because the way this works in MongoDB is you write to this proxy, and the proxy figures out by itself where the request should go. So if you have 3 database servers, you just say, I want to write this, and we'll figure out where it goes. If you use Postgres, you have to do this manually if you want to shard the data. So one of the big reasons for us was matching auto sharding, and it's a schema-less storage, and it does automatic scaling. But actually, in practice, all of this was really, really painful. The first of it is, Mongo is really slow once you run out of memory. Because all what MongoDB does, it maps a huge file from the disk into memory, and then there's the Linux kernel deal with it. And the Linux kernel has no idea what's in there. It's just random memory. And it has a really bizarre performance characteristic, especially if you run on Amazon. And it has this ridiculous storage overhead. So we have lots of numbers. So numbers are quite small. They're like 4 bytes, 8 bytes. They're not really that big. But our keys were like, I don't know, 12 characters. So we actually had more keys than we had values in our database, which was just ridiculous. And it has literally no query optimizer. So you have this chase thingy, and then you say, I want to get data that is according to this chasing specification. But depending on how you write this chasing specification, it might actually be an efficient query or not. It doesn't even try to optimize it. And it can only ever use one index. And it doesn't have any joins or anything of that sort. So it's just quite different to use, and very often you have to redesign your whole data layout just because you can't query it efficiently. And in many ways, it's just really, really immature. We had a situation where it was crashing on us, or when we were booting the whole cluster up, it was just randomly not booting, and there were regressions in maintenance releases. And at the end, we were just very, very disappointed with it. But the biggest reason we switched was because we spent a surprising amount of time writing things we could just use a SQL query for. And that was primarily someone having a bug in the game, so they wanted to know which users are affected. Or someone thought that, well, is this weapon good enough, or do we have to buff this gameplay weapon compared to everything else? Give me a report of all the player statistics. So you can kind of do that in MongoDB. You have this aggregation framework now. You have not particularly good MapReduce support, but it's a lot more complicated to use than SQL. And it's especially, you need a developer who writes this. And if you need to compare data from 2 different data sets, like data collection A and collection B, and you want to join this, you need to have a lot of memory to do this, because the database server can't do it by itself. So that was our main reason why we went away from MongoDB. The reason I'm saying all of this is because a lot of the patterns we're using for Postgres now are still inspired by how MongoDB works. So we basically built our own MongoDB on top of Postgres, which is weird. So the first thing you can do in Postgres now is you can store JSON data. The unfortunate part is that it doesn't work nearly as good as you think it would, because the JSON data type that Postgres has is just a string. It's basically a string where if you insert data, it will verify that it's JSON data and put it in there. But it doesn't do anything else really. It has functions to parse this, to get sub-documents out of this JSON. But if you actually see what it does, it's really, really slow. The good thing is that in Postgres you can use indexes on this data if you want. So it gets a little bit faster, but it's not a MongoDB replacement. The meta version is HStore. HStore is a key value store in Postgres. The unfortunate part is flat, so you can only have a key to a value, you can't have a key to another key value store, and everything is strings, so you can't really type them. It looks like with Postgres 9.4, which is going to be released in October, we might, if we're all lucky, get much improved HStore JSON support. But at the moment, this is just hoping that it comes. Nobody really knows what the state of it is. It looked quite promising that it would come. It's fully implemented as far as I know. But there's some, people are quite unsure in regards to how stable it is. So there's some waiting. But one of the things that Postgres has really good support for is arrays. And arrays get you really far. So for instance, if you have a traditional case would be you have tags on a blog post, then you wouldn't have to store them in a separate table. You can just put the tags into an array on this content object. And it gets you rid of a bunch of relations, which is quite nice because the data is very local. It's sitting right next to the data block when it's sitting on the disk. So when it loads the row, or if it has the memory, it doesn't have to scan anywhere around. It already has it right next to it, which is quite efficient and very, very fast. So yeah, there is some basic support for building your MongoDB in Postgres that you can build together with HStore, JSON, and array support. But it's just not entirely perfect at the moment, so you can't really get all that far. The biggest reason why it doesn't work is there's no upsert support in Postgres. So upsert is when you either insert a record or you update. And Postgres doesn't have it. And the main reason it doesn't have it is because it doesn't have a way to figure out what it has to log. So you can't say, I want to insert this record, because by the time that record is there, someone else might also have written the same one. So there is it can be emulated, but not particularly well. And there's some tricky parts of it. So I think this is, at the moment, the trickiest part about building something that looks like MongoDB on top of Postgres. But you can emulate it, and there will be an example later on in how it can be done. The other part, as mentioned, is until we have improved HStore support, you kind of need to use JSON type, but JSON type is not particularly fast. And the reason, again, is the key value store is flat in HStore. So if you want to have the full MongoDB experience, you can't really do this. And sharding you need to do manually. There's no magic auto sharding for you. But I don't know how many people actually using MongoDB's auto sharding. It doesn't really work all that well anyways. So you end up building your own one. And you can do the same thing as Postgres. Okay, emulating upserts. Until we get support for this in Postgres, this is literally the best you can do. I don't know if it's visible, but the general idea is you try to update the record first. If that works, you're done. If that doesn't work, you try to insert it. If that gives you a unique violation, then you just ignore it and you go back to the update in a loop. Do this constantly. And the reason you need to do this in a loop is because by the time you're done with the update, someone might fire a delete, for instance. So there is no way to lock this efficiently. You can lock the whole table, but that would be a little bit annoying. So you kind of need to do this in a loop. And that's at the moment is the best workaround. One way is to have it as a stored procedure, as a function. The alternative is to do it with save points. Save points are basically little markers in a transaction where I can say, I want to do something, but if an error occurs, please only go back to the save point, don't destroy the whole transaction. And in combination with the new exception diagnosis system, you can actually figure out which part of the transaction failed. So you can write this whole code to the client. So you can, for instance, say, try to insert me this record, but if it fails with a unique constraint violation, check if the unique constraint violation was against the primary key, and if it was, then you know there was already a record and you want to update it. And all of this is new in Postgres 9.3. So you don't need to parse error messages to figure out which constraint failed. You can ask the failure what exactly failed. Is it a unique constraint violation? Is it which column is it for, which table is it on, and so forth. So you can actually fully script this whole thing now. And if you Google around a little bit for upsert emulation in Postgres, there are a whole bunch of examples of how you can do this. So you don't need to copy paste any from those slides. Generally, the upsert part is disappointing, but what you win on top of MongoDB is MVCC. And MVCC is just absolutely amazing. Because the way Postgres does all of the things it does is when you modify something, each transaction sees the world a little bit different. The first time you fetch a data, this data becomes temporarily duplicated. So everybody else sees its own version of this. So if someone else writes a different value to this database, you don't need to lock anything because you have your own little copy. And this means that you have a lot less locking going on in Postgres than in MongoDB. In MongoDB, if you modify anything at all anywhere, it locks the whole table. So it means that only ever one person can write at the same time. And the only reason writes are really fast in MongoDB is because most of the writes only go to memory, they never hit disk. So if you actually need to hit disk, it gets really slow. In Postgres, you're actually quite fast because a lot of these writes are just very local. You lock one individual row, you don't lock the whole table. And there are lots of interesting patterns you can do with MVC. So I would, if you only need to support Postgres and maybe Transact SQL, the Microsoft SQL system, then you can completely depend on MVCC. You can do a whole bunch of things that are possible with that otherwise you would have to do crazy things with locking. So here are some things you can do with Postgres that are completely unrelated to MongoDB, but which are really nice. The first one is index expressions. And this is something that a lot of databases support now, but Postgres is, I think, the only open source database that supports this, which is really nice. So for instance, you can set an index instead of a column. You can set an index on a functional expression. So for instance, you have your user stored in their whatever preferred casing, but you can have a secondary index on the lowercase version of that. So if you compare it to a lowercase string, it will actually look at this index. Or you can have an index on the chasing expression. So the second part is an index on an attribute column, which is chasing, but on the sub-key location in it. And it will, when it builds the index, it will fetch this key and will put that into the index. So even if you use the very slow chasing type, you can actually have indexes that go into that chasing type, and you can use that. And the nicest part about all of this is you can have indexes that are a subset of your data. So for instance, if you have lots and lots of users, but your users might become inactive for some reason, you can flip a bit on the user and say this user is now considered inactive, and you completely ignore it from the index. Which means that if you only operate in a subset of active users, your index is much slower. And this is actually, can even work with a unique index. So you can, for instance, have the email address of users only unique for all for the active users. So the user goes inactive, it gets removed from that unique index, and the email address becomes available again. So if you only want to have each email address present once in the system. Or in our case, we do this with usernames. So if a user becomes inactive, the username becomes available for someone else to grab. You don't have to null anything out. In order to test these index expressions, if you try to explain it, like explain and then select a statement, you will sometimes see that they are not actually being used. And the reason for that is that Postgres only evaluates the usage of how it should use these indexes every once in a while. So if you want to test if your indexes actually work, you can do this. You can set enable sex time to off, which will not actually prevent sequence scans, but it will strongly hint to Postgres that it should actually use the index. And that way you can easily check if Postgres would even pick up your index, or if it might not do it. You should definitely not do this in production. It's a terrible idea to disable that, and it doesn't actually fully disable it anyways, but it gets quite close. This is, I think, my absolute favorite feature of Postgres 9.3, I believe. That's why it landed. It's the pgset statements extension. And basically what it does is every time you fire a query to the database, it internally normalizes the query and writes performance counters out. Once you have enabled that extension, you can basically select stuff. So it's the select user ID from users by email is something. But internally it normalizes the query to what email Postgres will work. And it writes that into an internal statistics table. So you can then ask that table for the total time divided by the calls, which is my average time this query takes, number of calls, rows query, and then it will give you basically a drill down of your slowest queries. And you don't have to actually analyze them every once in a while, look into your slow log. You can just have a background job that does this, I don't know, maybe once every hour or so, and you write this into RefWrite, for instance. And then you can plot out how slow your individual queries get. And if you see that the query goes up super linear, like it grows like a curve upwards, you know there's an index missing. So let's look at that. It's a lot of fun to use. You kind of need to hash your queries a little bit so that because the query statements can be quite long, so you need to find a way to show them nicely in graphite, but you can actually print them out and look at graphs. It's actually quite nice. In addition to PG set statements, which is the automatic query timing system, you can do explain analyze, which I guess most people know. Yeah, you prefix your query with explain analyze, but you can also do explain analyze from a JSON, and it gives you a JSON output of what the query system internally figures out should be used for this particular query. You can parse this and make little nice HTML pages out of it. And if you have your own application server, then you can just basically have a little thing where 2% of all queries will additionally be explained, analyzed, and then dumped out. And then you can also do a little metrics on your performance based on that. And it's really impossible to see, but this JSON output shows you, does it use a hash join, does it use an outlet join, that resorts, does it go to the file system. It gives you a whole bunch of information, and it will tell you how many rows it has to look at, which method it uses. So it's a lot of fun to just look at this and then draw out a little bit into small boxes to see how the database works internally. It's quite nice. The last part of this is what Postgres now supports for management and operations that some people don't know or missed in the changelog. One of them is streaming replications and point-in-time recovery backups, which is basically the ability to have a slave that is 100% synchronized with your master, and then you can flip over if you need to. And point-in-time backups means that you actually have a backup that is not just nightly, like half a day old or something, but almost instant. And for that, at the moment, there are a bunch of tools that help with both of these things. The first one is RepMGR. RepMGR is a collection of command-line scripts which allow you to script Postgres so that you have a hot second master that you can fail over to. So you have a hot standby. You press a button and they flip. And it fails over really, really quickly. So before Postgres failover took a bunch of minutes, now you can, I think, do it in under a second if you need to. And with a little bit of matching in your application server, you can actually do this without anyone ever noticing that you failed over to the other one. On top of the same system that RepMGR uses, there is PG base backup and Wally. Wally takes your basically your write-ahead logs and puts them onto S3 or any other backup system, any other storage system, and then you can create a second instance of your Postgres server by just pulling back that write-ahead log file. This is, I believe, what Heroku wrote for their Heroku hosted cloud Postgres installation. And PG base backup is basically a form of PG dump that dumps you out the whole Postgres folder, which you can just load on a different machine. And the nice thing about PG base backup is that you can actually make these backups of the slave. So all of the other backup systems right now can only make the backup of the master. PG base backup with a little bit of config tweaking can also make a backup of a hot standby, which means that you don't have any performance degradation when you make a backup. And you can restore them pretty quickly now. And for general enjoyment in working with the Postgres shell, there's actually a whole bunch of stuff you can do with PESQL to make the command line experience a little bit more enjoyable. The first one is you can make your prompts colorful and actually show you the state of your transaction. So for instance, the issue begin, in this case it gives a little star that you know you're in a transaction book, and it's colorful. And you can also set the rendering of certain elements to be more distinct. So by default, if you do a select null on PSQL, it gives an empty string, which looks like an empty string. It can be quite hard to figure out which is a null, which is actually an empty string. But with a little bit of Unicode, you can make the x null into a little x. And if you have an OS 10 terminal, you set this to an emoji, and then you have a little smiley face colors in your show. And if you set the line style to Unicode, it gives you nicer line rendering instead of ASCII. Last part, \x auto, which for some reason barely anyone knows, I think because it's hard to Google, makes the rendering of rows that come back automatically into key value pairs instead of huge tables that are so wide that you can't read them in your terminal anyways. For our particular use case, the main reason to switch to Postgres from MongoDB has been reports of arbitrary data. And this is really nice in Postgres because it's a SQL database and it's just more fun to write SQL than JavaScript that tries to copy data across. And for that, the biggest win is replication, basically, because you can have a whole separate database server which nobody cares about how slow it is, and you can do your analytics on it, and it's awesome. And the nice thing about Postgres 9.3 is that you can actually do this across multiple servers. So if you have your data set sharded into multiple hosts, you can have a different server connect to these through the Postgres federated database system, which is now 9.3. So you can have your Postgres server connected to 3 other Postgres servers, and then you issue a query, and it goes to all of the servers, collects the results, and merges them back in. It's almost like Mongo's, just it actually works with any SQL expression. The only problem with this one at the moment is that it's not particularly clever with the joins, so it's quite slow, so it's awesome to use for replication, but it's, I would say, not particularly recommended as a replacement for sharding, especially also because each of these database servers will have connections outgoing to each other database server. But the federated database is just a really nice feature. You cannot just connect to the foreign data wrapper is a really nice feature because you cannot just connect to the Postgres servers. You can also connect to completely other databases. So if you have a MySQL server running somewhere, you can have Postgres connect to MySQL and then fetch data from MySQL. Or you can connect to a Redis server and get Redis data into your Postgres thing. I haven't tried using this for connecting to Redis in production, but there's some really nice things you can do for analytical purposes. For instance, we have some of our access tokens stored in Redis, and by looking at which of these Redis access tokens are actually fresh, you can. I was able to optimize some of the queries for figuring out if I only want to do some users active in the last 24 hours. So I was looking at the access token in Redis and comparing that to data in Postgres. Alright, that's basically it for this presentation, but I'm very glad to ask any questions that come up with either Postgres or just our experience with switching from MongoDB to Postgres.
First of all, sorry for my English. Well, I didn't get it. Did you just move your schemaless data from Mongo to Postgres in a schemaless way, just columns of JSON or arrays data, or used it as a normal relation database?
So our migration path has been a little bit weird because initially the way we were planning on doing this was by looking, I don't know if you ever used Parse. Parse is a hosted MongoDB solution some people are using. And Parse has figured out that people put incorrect data into MongoDB. So what they did is the first time you write a record into the database, it remembers what type it is. So it builds a schema automatically. So we were thinking we can do the same with Postgres, and we actually did that. So we built something where you sort of chase it at it. It looks, oh, this is a number, this is a string, this is a list of X. And it automatically makes a schema migration to Postgres for that. That actually works, and it's not that hard to implement, so you can actually completely replicate MongoDB in Postgres without ever using anything like JSON or something else. But we actually figured out that it's a better idea to force people to use the schema than not to use schemas. So the way we're doing this at the moment is we have schemas for almost everything, and then we have certain blobs that are JSON. So for instance, when the system manages game sessions on our system, when a game manages game sessions on the system, we have player count is something the system knows about. The state of the session is something we know about. But then there's session attributes, which is just a data block. And people just write JSON data into it. And we actually don't have a filter by that either. But for analytics, you can still go in there and say, oh, I want to know what's in this JSON block. You can do something like that.
Thank you.
I wanted to ask about indexes on array. How the work can they use it for statistic queries like columns? So how effective are they?
So for arrays, you have a bunch of options. The first one is, in Postgres, you can define the index type you use for a specific thing. The default index is just a binary tree. It's completely useless for arrays unless you want to compare against that array. But there is a gin and a gist. Gin is a generalized index, and I have no idea what gist is, what it stands for. But the way it works, it basically takes each of the elements within an array and stores it in the index in addition. So you can actually do very efficient containment checks on arrays or subsets. And if you do a report, you generally do it over a whole bunch of the rows. And what you can then do is you can unnest the array contents into individual rows. So you can just, for instance, I don't have a use case right now, but you can take the individual items within a row and basically duplicate them out into individual rows and then do general group expressions on them, like aggregate, sum of them, whatever. And in addition to those, there are also array aggregate functions. So you can do a sum on array contents without even having to unnest it. So there's an array sum function, I believe, and a whole bunch of other things. So you can do quite good operations on those arrays.
Sorry for my English. I would ask about storing null values in database. Is it bad practice to store null values, manual null values in your table?
So we store tons of null values. The reason for that is that Postgres has a really, really nice feature, which is it can do a schema migration. First of all, it can do a schema migration in a transaction. And it can do a schema migration without rewriting any of the data for as long as the new column is optional. So if it's nullable, you can add a new column to your schema, and it takes like a millisecond or something. And it's more than a millisecond probably, but it's a very fast operation. So as per policy, all of our roles, all of our columns that are not completely system critical are completely nullable. So we actually store tons and tons of null values. And our data layer will then take these null values and fill in the default later on. Which means we actually never store the defaults, which means our migrations are really, really fast. It's probably bad practice by traditional database management point of view, and not every database administrator is probably happy having partially weird data in that particular database, but it's actually not really a problem for this. One thing we do, we use the more or less function, I believe, in expressions, which basically, if the column is null, fill in with some other thing. And we use this very, very frequently to fill in null values with the intended default. But yeah, it's nulls everywhere.
Enjoy my English. Sorry, I want to build a SQL application which based on maybe special data, and what should I choose? Maybe Postgres or MongoDB, and maybe can you compare two-dimensional indexes?
So the nice thing about Mongo is you don't have to think at all. The problem is if you... So I wrote a blog post last year sometime, I wrote SQL is agile or something, where I said that with SQL, even though you have to write schemas, you're actually much more faster in iterating something, because if it actually grows a little bit too far, you can still solve your problem with SQL without having to rewrite all your data layout. One thing we noticed with MongoDB is that even with tiny, tiny data sets, quite quickly do you have your data laying out in the wrong format, and you need to do some trickery with it to actually get the data out the way you want. And this is, someone can argue that this is a problem with you not designing the data layout properly in the first place, but sometimes you don't actually know what problem you want to solve until you have that problem. So one of our examples was we had sessions and session slots in that session. So you have a session object, which is just a dictionary in Mongo. And then there's an array in it, and each array member is the player in that session. Which was really nice to figure out. Like you can append a player into that session, you can get the player out of that session. It's quite nice. But what you can't really do, at least until the aggregation framework came around, you couldn't say, oh, give me all the sessions I'm in, because that was just normalized. You can do it, but it was just really slow. And for that reason, I think that if you have a somewhat normalized data layout in SQL, you're probably much faster in making a small little project, because you don't have to spend any time redesigning your data layout. You just have it somehow normalized. And if it's too slow, then you can just try to denormalize it a little bit. But then again, my bias is towards SQL just because I wrote a ton more of it, so I know how it works and what I can do with it. But I would strongly recommend probably going to SQL for a small project, just because it's almost impossible to run yourself into a corner.
Postgres. You said that MongoDB is moved for heavy write workloads. In this case, I agree with you that NVCC in Postgres is very nice for writes, but I know that MongoDB is much faster for reads than writes. Can we compare the read performance of Mongo and Postgres?
So in our case, Postgres is faster, but that's probably just a side effect of us having lots of numbers, because we have to send a whole lot less data from the file system into the database. And the biggest problem we had with MongoDB read performance was that once the data became too large for the RAM size, then when you run on Amazon, all you off in regards to how performance is. Because the Linux kernel has to manage all of your data layout, and it's basically just an MM file. So every once in a while, just weird things happen, and the MongoDB query took like 20 seconds instead of 100 milliseconds. And that was usually just because you were unlucky, there was an fsync going, and at the same time, something needed some data that was not cached, and it just... We haven't seen that with Postgres, so it's a win for us, but I think if you don't run on Amazon, then probably you can see much different numbers from MongoDB than us. I would definitely not particularly recommend running MongoDB on Amazon, at least not off EBS.
How many things did you have to build customly to actually emulate behavior of MongoDB in Postgres?
I'm not entirely sure because we threw a whole bunch of code away. So we built this idea initially to automatically derive the schema out of the writes. That turned out to be a feature we no longer use. So we have a whole bunch of code that's completely dead in the water. The most complicated thing to replace for us was the lack of upsorts. And for that particular feature, the upsorting, we have a custom expression language where you say, oh, I want to increment the number by 1. And then internally that compiles into some sort of if row missing set to 1, otherwise update with row value plus 1. And this whole system is more complicated than it needs to be. But I would say our whole database access system written in Python is probably less than 1,500 lines. So it's not that much code. But yeah, there's some things in that. It takes some time just to figure out what you want.
раз больше нет вопросов. Давайте поблагодарим докладчика.